Welcome back to my YouTube channel. Hope you are doing well. In this typical way of this typical question, we'll be dealing with we're still under strength of material N6, still under maximum bending moment on shafts, right? All right, so which is our module 3. So we've given here example 3.3. Read as follows. Says a solid shaft with the weight, you see the weight of the shaft its own, is used to drive shaft between bearings which are 1.5 apart. Remember, the bearings are reactions. I've told you bearings are reactions. Always bearings act as reactions. You must please understand that bearings always are reactions of the beam or of the shaft, but they become reactions when you are doing or sketching the beam. I've said this. The bearings, they are reactions, they act as reactions, right? So we have again says the shaft, you see those are 1.5 apart, okay. Then the shaft supports a flywheel and the belt drive. You see we have a flywheel here, and the belt drive is vertically below the shaft. Vertically below, guys. When it's vertically below, what we do? Vertical below, we're adding like is vertical below. We'll discuss about that. Our tension at the acting downwards. Vertical below, the pulley also will act downwards. So, but we'll discuss about that. We did discuss about that, but we'll see as we're doing this question. Below and the belts are parallel. We see the flywheel is placed 0.5 from the left, 0.5 from the left bearing. The drive is 0.5 from the right bearing. Check them. The weight of the flywheel is 2000 newtons, and the weight of the pull is 275 newton. The third side tension and slack side tension belts are 2000 newtons and 100 or 1000 newtons respectively. The weight of the shaft is this 100 newton per meter. The uniform distributed one. Says number 1, determine what the bearing reactions. All right, guys. All right, are we still together? All right, so food was still together. Look, hopefully I did not lock this. I locked this page, but okay, it's still going down, ups and down. Oh, okay, it's fine. Okay, we have now, we see they want the bearing, guys, the bearing reaction. So let us scratch our beam. Maybe you might understand if we try and scratch the beam. Right here is this beam, guys. If I can try and scratch the beam, maybe you might understand. All right, let me do like this. Right, scratch the beam like that. All right, so we have our beam. Says from the bearings, remember those are reactions. The bearings, they say it are 1.5 apart. 1.5 apart. This whole distance, I still remember until when you go, this is 1.5 meter apart. This whole distance from there until there it's 1.5. Is this will say reaction 1. Remember, these are bearings. Reaction 2. Then what does it say again? Remember, remember this, it says the beam. You must not forget that what I'm trying, this, it's I can say it's this thing, it's the weight, it has the weight of the shaft is 100. It's uniformly is like picture it like this, guys, because it has that weight, this weight of this, whereby the uniformly distributed, whereby it's 100 newtons per meter, right? That is 100 newtons per meter. This, let me write it there. This is 100. We have that 100 newtons per meter, because obviously this is our distributed wire. All right, but let me just do like this for the sake of not confusing. Let us put this in details some more. It's one apart. Okay, we know that the flywheel is 0.5 from the left hand, and then the belt is 0.5 from the right side of this right hand bearing. So here from like 0.5 from this point to go like that, we'll have some force there, which is 0.5. Also from there going here, we'll have the force there acting 0.5 apart, 0.5 meter from the bearing, 0.5 meter from the bearing. Remember, this will be the flywheel. This one will be the flywheel. This one, let me just do this. The one that I'm writing, I will indicate with black that it's our flywheel. That will be the flywheel, right? So we're supposed to know it's, let me grab this a little bit below like this. All right, that is our flywheel. Then here we'll have our reaction, that which is we've given 2000 of the. All right, this is what we have, guys. So by the way, we know it says that we have that flywheel is 0.5, and then what is they say flywheel is 2000. We know, I can say right here 2000 for the flywheel is 2000 newtons, the force that is acting there of the flywheel. Okay, it's from the sorry guys, not from the, says it's here, it's 2000, because it is acting from the flywheel is acting from the left. This is 2000 newton is acting from the left, the flywheel. Then here from this side is the pulley. We have a pulley flywheel, you see, from the left bearing. Now pulley, guys, the pulley, remember the pulley, it will consist of what, of tensions like this. Here will be weight of the pulley acting down, and this maybe here will have T1, T2, the weight of the pulley there. We'll have to find the weight. Now we cannot just write it as it is. You're supposed to find it's acting below. So since it's acting below, we know that to find the force of the calculating the force of the pulley, this one that is acting there, we'll say FB, force of this bearing, not the reactions, will be equals to T1, I've discussed this, plus T2, because remember they are acting downwards, guys. The weight of the pull is always acting downwards, so this is like some force, like vectors, they are pointing on the same direction. We are adding, they're acting, the forces here are like vectors, guys. So another form of vectors, we add that the pulley, or the weight of the what, of the pulley, guys. of the pool like this. So T1, we know that it is 2000 plus T2 that side, which is 275, plus now the weight of this T. Okay, yeah, I've made a mistake. T2 it's what? T2, just that here. T1 and T2, this is 1000. The pool is 275. Okay, there I add 1000 plus 275, then this will be equals to what? Punch them will be 3275 watt newtons. This will be the force here, is 3275 newtons. All right, this of the what? This is a pool, remember guys. So this is what we have. Now we have your beam like this. This is how it goes, guys. This is how cookie crumbles. So what do they say? They want the reaction of the bearing reactions. We want the reactions, guys. Supposed to calculate the reactions. Now we know this is our beam. Now we are answering our questions. What do we know about the beam? We apply the bending moments. Bending moments, guys. So we apply the bending moments. I can take the moment about reaction 1. Can say R1. So we know that when you take the moment, some of the clockwise moments or some of the anti-clockwise moment is up to you. Which one do you prefer, right? I can say some of clockwise moments also, because I have some there. Let me just sum off. Can take, it's up to you which. Can say sum of clockwise moment is equals to the sum of the anti-clockwise moments. We know that, guys, by the way. So these are beam clockwise moments. You know how to calculate the here this reaction. This one on the top, the one that acting clockwise will be this one. we know how to calculate, guys, the beams, guys. By the way, we know how to calculate our reaction. Isn't it? We know how to calculate the reaction. So let us deal with our reaction, guys. We know how to calculate the reactions, right? And then do not forget to have what is that? The distributed load. Remember this distributed load. Do not forget about this distributed load. Is 100 here. We have a distributed load here. This is a distributed load of 100 Newton meter. Do not forget about it. So you can even convert it if you want. You can say 1000 and multiply this by, let me check, how 100 multiplied by this, what I will have. I wanted the middle, but if we want the middle, multiply again by 0.75, but we will see that. We'll see. Let's just do this, what we want here. Okay, we have, or let me just start. Okay, one, the forces that are acting clockwise 200 will cause the beam to rotate in this direction, and also that one will cause the beam to rotate in this direction. Remember, here in the middle we'll have also the weight, the distributed load. When you convert it, you'll have the force again that will act like that. We'll convert it on our calculate. So you see we have 3 forces, so that will cause this to rotate clockwise. All right, so we have 2000 multiplied by this distance, which is 0.5. Are we together there? Plus we have these guys now, this 3, this will take the distance there. What will be the distance? 1.5 minus 0.5. I want the distance from here until there, till the end. Let me check. Simply 1.5 minus 0.5. That distance is simply to be, it seems to be what? It's just, it's just 1. It will be 1. Remember, 0.3. Actually, also this distance, that means this distance from there until here again, yeah, will be 0.5. So this distance there also will be 0.5. I just wrote this far a little bit, but will be 0.5 because 0.5 plus 0.5 is equal to 1.5. 0.5 plus 0.5 plus 0.5. All right, this will be 0.5. Would be 3275 multiplied by 0.5. Remember, the whole length of this beam is 1.5. Already we have 0.5 here, and also here we have 0.5. 0.5 plus 0.5, it's 1. Clearly, the remaining is cleared. That is 0.5 also. So, yeah, then plus, here is a problem now. Consider this, we have a distribution. The distribution also will act clockwise, guys. Will point downwards. Will act clockwise now. Remember this, I will take as a, can write it 100 Newton per meter there. Maybe I will show you that force there, here, which is acting there in the middle. So to show that, remember now it's in Newton meter. We'll say 100 is, it's in Newton per meter multiplied by the whole. Remember, it's distributed for what? The whole beam. The whole beam multiplied by 1.5. But you want to place it here exactly in the middle. We want to place that force exactly in the middle. You'll multiply that by what? By the half of 0.2 or 0.5. Half of 0.5, guys. 1.5 divided by 2. What is that? 0.75. Again, you multiply this by half. You want this to be placed there. Multiply that by 0.5. So that is what we have. Actually, this is an N4 stuff, the prim and stuff. Yes. So this is what we have so far, guys. Right. This will be equals to what now? The anti-clockwise one. Remember, we've taken reaction here at 1. Oh, you understand? The anti-clockwise one now will be, this will rotate the beam at that direction. Anti-clockwise will be reaction 2 multiplied by the whole distance, which is 1.5, taken from that. All right, now let us find what we're supposed to get. So you know, here I want R2, I'll divide by 0.5. You add all of these add all of these there, then you divide by 1.5. so let me just show you. 2000 times 0.5 plus 3275 times 0.5 times 100 times 1.5 times 0.75, divide this by 1.5. so what are you going to have here? Reaction 2 will be what? The value of reaction 2 will be 2 9 reaction 2 will be, if you punch that, will have 2 9 2 5 Newton, like this is measured in Newton. 2925 newtons. We have reaction 2 so far. Now it's easy, you can use some of that. Now you take the moment about what now? About reaction 2. You take the moment about reaction 2. Now if you take the moment about reaction, you just swipe this thing around, guys. You just swipe this thing around. If you take that, just swipe everything around. So if you take that moment now, this will be the same thing. We won't change anything here, but you just have to change. We swipe this thing around. But okay, let us take that moment again. Let us take the moments. You can take them, the moment, some of the moment. Can say some of moments. We have there some of moments where can say sum of clockwise moments again is equals to the sum of anti-clockwise moment. So we're taking reaction about now, we're taking moments about reaction 1. All right, so if you take reaction 1 there, here it is, reaction 1 and reaction 2. Okay, we started by reaction 1, so we should take this about reaction 2. Today I feel like I'm tired, today I'm just tired, guys, so be patient with me. I'm so tired. About reaction 2, if you take that, all of these will act towards these beams. Now what will the force that will act clockwise will be R1. All of these will act where anti-clockwise. This one will act anti-clockwise. So let's check there. We'll have R1 multiplied by the whole length, which is 1.5. It's equals to 200 multiplied, we have this 200 here, multiplied by 1 from here until this is 0.5, and add this 0.5 by 0.5 will be 1, this distance, and from 200 going there. I know that that is become messy now, but as you know, guys, this will be 1 multiplied by the reaction, this one, which is 0.5, that distance there, plus, why I say multiply, plus that reaction of the flywheel, which is 3 2 0.75 multiplied by 0.5 plus the one of the weight, guys, distributed load. We know that is 100, multiply that 100 by the distance, by the whole length, multiply also by the half of this length, which is 0.75. Then we have the reaction one. You know what you're supposed to do. You divide all of this by 0.5. You will get that reaction one to be 2500 Newton. This is reaction one. So we have that reaction one. So we have this, guys. The aim now, we have this here. Let me just sketch now our beam now, the full. Let me just show the one that now it has all of this package. We have everything now, guys. Here we've calculated this is 2050 Newton. Here we have 2925 Newton. We found that this. So this distance from there, this distance until there of 0.5, we have some force here. We have the force that is acting there, 0.5 meter. Also here in the middle we have 0.5. We have another 0.5, as you have seen there, 0.5, 0.5 meter. Those are in meter. Here we'll have another force that will be acting there. Remember we had 2000. The one of the flywheel of the pulley is 3275 Newton. All right, this is what we have. We have this. Why I'm throwing this now is full. Why we're supposed to find this is because, guys, we want to calculate the maximum bending. Well, the reaction we're done. I think now I'm under question. We found this reaction. I think now, okay, we did now question one. I think now we're here now question two. Determine what? Calculate the maximum bending moment by drawing the shear force diagram. Okay, maximum bending moment. You want to calculate the maximum bending moment by drawing the shear force diagram. All right. We want to find that. So we're supposed to draw our shear force. Okay, you still remember the shear force. Let me try. We want to draw the shear force. Right. We want us to draw the shear force. We can do this to become our zero reference. Yeah. Obvious. First we'll have 0 there. 0. We know that the force is going upwards. Of the reaction will go there upwards. All right. We have that will go upwards for 2050 Newton, 2050. Then we have, remember this is distributed. By the way, we have the distributed load here. Then so if we have a distributed load, you'll have the line that's sliding like that. So we'll have the line which will slides for that 0.5, but will slide, we'll say now 2500. This is facing downwards, minus 2000, right? Minus 2000. Or 2, sorry, we went up, so one to here we're supposed to have some to go to this part there. We have some force again here. Remember, this is distributed. We're supposed to have some force again there, which is will be 100 multiplied by 0.5. 100 multiplied by 0.5, which is what is 50. It's 50. Here we'll have another force between there, which is will be 50. Then remember, between the distributed, if you still remember your beams, so 2,500 minus 50. You slide for this distance, we go there, over there. This is what we have there. Now we go 200 is somewhere here. If I estimate somewhere there, then I can go there, somewhere there. All right, there will have, there I'm having 2000. We'll have 2,400, 4,450. There, remember, those is in Newton. We know that here, straight here, as you can see, we have 2,000. 2,450 minus that, we'll have 450. 450, maybe will be somewhere here. Let me go and maybe somewhere there. Maybe there. Somewhere there. All right. We'll have 4,000 or 450. All right. So we have to slide again from here in the middle. You're supposed to have the force here. Remember, 0.5 for this portion. For this 0.5, we'll have 50 again here. 50 newtons again here. Also here we will have some force here that is acting there, which is 50 newton. Remember, we'll say 100 multiplied by this distance, which is 0.5 there in the middle. Then we'll have 50. We subtract again 50. We'll have 4,000. For that length we'll have 400. Sorry, 400 until somewhere here, just before it touches yeah. Oh, that is so straight. No, that is very straight. Let me just go a little bit. That is very straight. I want a slanted line a little bit. No. Okay, let me do like this to find a slanted line. Hopefully you will see what I will do. Okay, let me take this. Yeah, I think this will be better. Hopefully you will see there. Will be somewhere here. Must line a little bit there. So there we'll have 400. Okay, then we'll subtract straight 400, subtract 3,275. We'll have negative 2,875 going where? Downwards. Going downwards. Will be acting. Let me just sorry guys, I have no space. Let me take this on the bottom. Let me just take this on the bottom part. No, what I'm doing there. Okay, let me do like this, guys. Right, then I do like this. I want to take all of these to the bottom part. Alright, then I do like this. Okay, let me drop this here at the bottom. Alright, this is what we had, or this is what we have. So going down like this, vertically down, here we have our 2000. Well, vertically down like that, we'll have that 2000. Right, we have that is 2000. We have these guys there. Yeah, will be a little bit. Let me just put it here a little bit. All right, this will be negative 2875. All right, so this is what we have. Let me wrap this thing. Let me write it here on the side, guys, or here in the inside here. We have negative 2875 here. Then we slide by then there we're supposed to slide, we have 50. You say this minus 50 again. If you minus 50, this will be negative, 925. Supposed to slide that distance, then I slide for that distance there, maybe somewhere here if I guess. Right, there will be negative 2925. Then obviously here we have what, upwards, the positive. This is going upwards. Remember, if it's going upwards now, we are adding. If we add now, adding this to that will come to 0. This will return back. It will return back to where, to 0, like that. It will return back to 0. So that is what we have so far, guys. So why are we calculating this? Why do we draw this? Is because the maximum, guys, the maximum bending moment is acting, it's at the position where the shear force diagram, where the shear force cuts at 0. It cuts where it cuts is here at 0. That is where we'll have our maximum. So our maximum will take place there. The maximum bending moment will take place there where it cuts at 0. It cuts at 0. And then this distance, guys, we know all those distance. This distance from here until there is 0.5 meter. All of this distance we know is 0.25 meter. All of them we know those are 0.25. It's cut there Why it's useful is because, guys, maximum bending moment, when you have given that beam, distributed beam like that, you take the force that is next. You take the moment about the belt pull, considering the force to the right. Take the bending moment about the pull to the closest. The force that is the close. Yeah, you take the one where it cuts is there. We'll take the closest point there from the zero. We're supposed to take these, guys. I will take this. I will use this, guys. We'll take moments from the right. If I take that, I will have. We know that is what we have. So it cuts there. So I will take it. It's up to. I will take it from. I will use this diagram here. I will take the moments here using this. If we take the moments here, we have 2000 less, and then I take this. This side guide is what. Taking this from the closest point where it cut is cut here, and goes it cuts here. That is where we have our bending moment. That means bending moment is there at that point. It's cutting there. So the maximum bending moment, if after calculating this, all that I know will be reaction that is close. I don't know, maybe I can call this reaction A multiplied by we're supposed to become reaction. To find this will be reaction 1 or reaction 2 is up to you. You can call this N, but the closest one, the formula for that will be reaction multiplied by A. I will call this A, it's a length, minus the weight multiplied by A. The A is the length multiplied by A divided by 2. That A represents a length. What I'm trying to say, this formula that will use the reaction, or here you see we have a maximum. The maximum cuts here. Where do we have the maximum shear force? The minimum, the one there's negative there at the bottom. I will take it from. It's up to you guys. Actually, let me not talk too much. You know what you're supposed to do. I will use this, guys. This reaction, the one that is close to that, I will take it from for I'll take the moments about the belt drive. I'll take the moment about the belt drive considering the force acting to the point, so no problem. So the point there, I have that to be 2925 multiplied by A. I said it's a length. It is the length. That length there, the length. The maximum, remember guys, is maximum bending moment is acting there, as you have seen, guys. Here it's acting here at this distance. It's here, is there. That means from there until where the maximum bending is acting is 0.5. Then I'll multiply this by 0.5. That is A. Subtract the weight. Is a weight. The weight of the shaft, the distributed will load, this W. I'm talking about that. The weight is 100 Newton, isn't it? 100 Newton per meter. You multiply by this is the whole length of the shaft. Not the whole length. For that length that you are taking the moment, the 1000. Remember, we have this. We're supposed to consider this distribution load. Here it is there. Supposed to calculate this, or we can use that 50, but I'm just using that. We'll have this from here. We take it here. We have this force again here. Supposed to have that, or we can say 50, but already you can say 100 because you want to convert this distributed to become a force. But already I've shown that force there already, but no problem. Let us use this is 100, right? 100 multiplied by this length, and then the half of this length. You want this, guys, will be that length is 0.5 multiplied by the half of it. The half of this is 0.25. Actually, what do we want? We want the force, the reaction here. We know that from we taking, considering this part, guys, from here where it's until there, we're taking there, we have this, we're taking it from to the, what is this, we're considering this portion, our right hand side, we're taking to the right, we're considering the force on the right. From here where the bending moment is acting here, the maximum bending moment, as you have seen, then considering all this force, we use our bending moment because it's acting there. So if I'll get this maximum bending moment to be 1,450 Newton meter. All right, so this is how you'll find this. This is how you get these, guys. This is how it goes. You find you draw your shear force diagram so that you'll see where the maximum bending moment is acting at. You can also, there's no problem, you can also take it from the left, but we have many forces. I've decided to take this considering to the right, the bending moment about the right side, because I only have one force here, and then I have only two force, but here we'll have many force. It's up to you, take it from the left or from the right. So I took this from the left because we have this force, the maximum, we have this force and only this force. If you take it from the left, you'll have this force 50, 2050. You see, there are many, so I just took this from the, I've considered to the right. We're taking point the moment until here where it's acting. We know the bending moment, the maximum bending moment is acting there. We'll consider that. So this is what you're supposed to have, guys. By the way, thank you for watching. And then today I'm tired, guys. Sorry if I've not explained good for you, but hopefully you've understood a little bit. I will do some more videos, guys, so that maybe you'll understand. All right, so guys, by the way, thank you, guys. Thank you for watching. And may you kindly subscribe to my YouTube channel, become the part of the family by subscribing to my YouTube channel and click the notification bell so that you'll be notified whenever I'm posting a new video. I will sleep a little bit, then I will wake up fresh. Then I will record some videos, guys, based on the sharp, so that I will explain more. I will do some more of videos, guys. If you have subscribed there, you'll be notified, and click the notification bell when I'm posting some video. You'll see I will do some more examples, so that you'll understand this. And then in our next chapter, I think we'll focus on equivalent torque and equivalent bending moment, where we're looking at principal stresses, the combination of the twisting and the bending moment, right? So all the best.